Am I loud enough? All right. Thank you. Well, thank you very much, Jerry. That was certainly an impressive introduction. Hope I can live up to it. I'd like to start off by telling a little anecdote about Hewitt Phillips. A short time after I joined the flight division, and he was researching yawing oscillations of aircraft. He had set up a simulator in which he could vary the frequency of the oscillation and restoring forces. And the pilot was supposed to try to damp these oscillations with pedals. And I was one of the subjects, not the only one, but I got in this day, and they'd pluck it and the thing would oscillate, and I'd try to get out of phase with this thing in order to damp the motion. And I found that 9 times out of 10, or 50% anyway, I amplified the oscillation. So I decided to wait until this thing got to its maximum amplitude and then put on full pedal till it stopped. Well, I did this about twice, and there was a bang and bang, 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 bang. All the springs from this thing flew all over the hangar. And Hewitt came up to me a little bit red-faced and he said, "That's not the way you're supposed to control it." Anyway, I was born in the Upper Peninsula of Michigan, and of course, my dad was a mining engineer. There's copper and iron up there. And I saw very few airplanes. We moved to Canada, though, for 2 years into the nickel region around Sudbury. And some great big old biplane flying boats of World War I, namely Curtiss HS-2Ls, were bought by or given to the Canadian government by the U.S., and they used them for forest fire patrol. And I could hear these things coming low over the forest. We were out away from the city. And these guys would fly by at about 200 to 300 feet, and the observer in the front, which used to be a machine gun position, would wave to us kids down. Well, kids, there weren't very many kids around me. Most of the time I was alone. And I'd wave back and so forth and watch it go off. And they'd repeat every 2 or 3 days. And that's when I really became interested in flying. Moving back to the Upper Peninsula, I used to attend some of the Michigan Air Tour shows where there would be a collection of airplanes, but I was quite fascinated. By the time I was in high school, or 9th and 10th grades actually, I had decided I wanted to be an engineering test pilot. But I realized I had to get an aeronautical engineering degree, and then I wanted to proceed to the Navy flight training because the Navy operated more types of aircraft than the Army did. Well, it didn't all quite work out that way. I did go to the university and entered in 1934, aeronautical engineering. And during the course of those studies, I wasn't a very brilliant engineer, by the way, but during the course of those studies, I sneaked. My dad wasn't exactly enthusiastic about me flying. But anyway, I did join the glider club for about 1 year, I think it was, the junior year. And we didn't get very many flights. Most of the time, the glider was being worked on. But first, they held us up in a strong wind at the wingtips, and we operated the controls to see how they functioned. And then we towed by truck. Well, on my first tow, I had been used to steering a bobsled, where you turn the front sled in a certain direction. I had read a lot about aviation, all the books, Wolfgang Langley and Stick and Rudder, you know, and this sort of thing. But the thinking couldn't overcome the habit. And so I started down this runway doing all the wrong things with the rudder, and the first thing I knew, I was airborne. And then I could give up the rudder and flew it with the stick cast off and glided gently towards the runway and just eased back the stick and landed. So I got over my fear of soloing on the very first flight, which I'm thankful for. Let's see, at the University of Michigan, I did join this glider club. Could I have the first slide, please? One of my friends and cohorts took this picture as I was landing one day. It looks as though I know how to do this by this time. The little white thing in front of me there is the airspeed indicator, just a flat plate mounted on a spring, and it read along a scale. But you could take that nose off and be out in the open. Well, I never did proceed to soaring. They did soar in the summertime with this thing. Next slide, please. I'll learn. When I arrived here at NASA, by the way, the professors had been coming down to Langley here, some of them, to the conferences, but also to work. And they were very enthusiastic. They selected 3 University of Michigan people along with 3 MIT in that selection. NASA had just gotten authorization to expand. This is the early part of the buildup of German forces in Europe. And the new labs were yet to come, but they had just begun this, and they were recruiting for the first time. And I got here on June the 2nd. Some of my MIT friends got there June the 1st. But I reported out to Elton Miller, and he said, "Now, where would you like to work?" I said, "I'd like to work in the flight division." He said, "Sorry, we've got you slated for the full-scale wind tunnel." So there I spent 4 1/3 years. This particular airplane is the Brewster XF-2A1. It had won the competition over Grumman for the Navy's first carrier monoplane. And it had had such poor performance that the Navy had asked NACA, I'm sorry, I've had more years at NASA than I have at NACA, I forget sometimes. Anyway, they asked NACA to put it in the full-scale tunnel and look for ways of improving the performance. Well, they found a lot of them. The cowling was poor, the carburetor intake caused separated flow, it had high drag, and so forth. And the interesting thing is, it was just being completed when I got there. And after that, some 30 aircraft, military aircraft, passed through this tunnel for improvements during the war years. But this was the first one. And later, of course, Brewster failed to produce, and Grumman, who had continued to build the F-4F despite losing the contract, really took over, and the F-4Fs were the aircraft produced in quantity. It's interesting that the second airplane tested in the tunnel after this was Grumman's latest biplane, the F-3F, and it was 115 mile, no, it was a, well, it was 25 or 30 miles an hour faster than this monoplane. Next. Oh, I'm sorry. Well, during this period of time in the full-scale tunnel, by the way, they had about 6 landing fields, civil landing fields around here, but this landing field is where the Copeland Industrial Park is today. It's really in Hampton, but it bordered on Newport News. We had learned to, we had bought this airplane and flew it out of Morgan's Field, where the military highway down here, Mercury, crosses the Langley Field Road. And however, the man who owned it got rid of his cows, the grass grew too high, and it was an arresting gear and made it pretty hard to take off because the engine seemed to burn grass seed. So we moved over to Newport News where they had some hangar space. This is really one of the early fly-by-wire aircraft because it had cable control, of course. Well, this is a little premature, but I'll leave it on. During 1941, Melgoff, chief test pilot, detected the fact that it was becoming difficult to get the kind of trained pilots that the military forces were producing. And he thought that he'd better make some provision for supplying and retaining the staff of test pilots that the Langley Center had, considering that Ames was requiring pilots, Cleveland was requiring pilots, and those are both being activated in 1940, 41, 42 time period. So he wrote a memorandum asking permission to select some pilots or some engineers who were eager to fly and were best qualified to be taken on board as trainee test pilots. Now, bear in mind that there were no test pilot schools in that day in this country. The Empire School had not been set up in Britain yet, but Germany had a course in test piloting. It was a 4-year college course, and you could specialize in either flight test engineering in the last 2 years or test piloting. And so they were producing trained test pilots, but we didn't have access to them at that time. So this was the one on the left is myself, and over here is Bill Gray, a much shorter little fella, but he had more experience than I had. He was taken on board about the same time, although he was able to transfer. I had to finish up some work in the full scale, so it took me a little bit longer. But Herb Hoover's on the left. He was our first X-1 pilot. killed in the crash of a B-45 here, our first death, I think, on the left, and Mel Goff, who very shortly after this became chief of the Flight Research Division, and Bob Gilruth was his assistant. Now, you heard Hewitt talk about these light airplanes with which NASA did a good deal of research in the 30s. They did, because they could modify them cheaply and they could do it quickly. They used tapered wings, 3-to-1 taper and so forth. This one is a Fairchild 22, doctored up by the Navy, Warner engine, but notice the full span flap clean across the wing and the spoilers for control. So this was one of the airplanes. There was a Ryan ST, a Stinson SR-80. They had some SNJ and T6s too, so there was a step-up sort of ability to train and get familiar with things. Now, we always sat down before flight with the pilots and engineers and listened and asked questions after flight. And, of course, when we were assigned projects, we worked very closely with the project engineers. And I must say that safety was built in at the very low ground level. Both Gilruth and Goff were very highly safety conscious and made sure the project engineers designed for safety and monitored safety throughout the whole program that he or she were familiar with. We were also we were put through a training program that was to develop versatility as a pilot in flying the aircraft, and also the ability to check ourselves out responsibly. Okay, now in the first year after I joined the staff, I flew 19 new aircraft to me, 9 of which were fighters. And the first fighter I flew 5 months after I joined the staff. That was this one, which Hewitt Phillip talked about. And here it has the all-moving tail. However, I flew the airplane when it had the fixed stabilizer and the elevator. But later I had a chance to fly this arrangement. This airplane had been used for cowling research to start with, and then was converted to handling quality. I was responsible for my own checkout here. I read the manual, asked the questions I should have of the various people, and it was interesting. I walked down this day ready to check out, and I climbed up into the cockpit, went through my check, and as I was ready to give the crank signal to the line crewman, Hoover jumped up on the wing. He said, "Just a minute, let me look over the cockpit." So he examined everything he'd misset in anticipation of my arrival. He went through the whole thing to make sure that I had cleaned up the cockpit and was really ready to go. So then the only guidance I had was, on the final approach, set up a speed of 120. When you get to flare height, cut the throttle and land. So that's what I did. But one of the interesting things was that I was prepared for speed, I thought. The airplanes I had flown didn't move along at such a high speed. I came into the pattern allowing myself, I thought, plenty of room. But when I started turning final, I realized that my turn was very cramped. I hadn't really allowed for the radius of turn because of the speed change that I had not been used to. But anyway, the landing went very well. I just had full flap landing gear, closed the throttle, and just flared nightly, easily to a 3-point landing. So that was a success. And, of course, that makes you feel very great for the moment. My first project was a Navy XS BA-1. The Navy had supported NASA in a study of different size control surfaces and the ratio of movable surface to fixed surface. In this case, it was a study of dihedral effect. And of course, in those days, you didn't adjust these things with electronics. You changed the airplane. So that we took the wings off and put shims in there and bent the wings up, and it has a very high dihedral. And for the test runs, I had been assigned the project in general, so I had been flying it for a while. I went up looking for a cold front, which was moving down our way, to get along the roll cloud. So that's what I did. I tried not to get heavily involved in the cloud. Sometimes that's difficult not to. But anyway, I don't remember that this thing had the high dihedral had any adverse effects. XP-51, I can't pass this by. I had flown in the first year a P-51B. But this is noteworthy. The British Purchasing Commission in 1940 had come over here to buy more airplanes. They were short of airplanes. And they had gone to Curtiss and Bell, and they were choked up with supplying the U.S. Army. So they went to North American. And North Americans said, well, British asked for North American to tool up for P-40s. And I said, no, after a day or so again. They decided, no, we'll design you a better airplane in 120 days, but we will not tool up for P-40s. So they submitted a design to the British, and they bought it. So they went to work to produce the Mustang 1, of which this was one. Now, there was an agreement that the U.S. government would receive 2 of any product that was produced by a company for a foreign government. So this was the number 1 U.S. XP-51, but it was the number 4 Mustang 1. And the other one was number 10 off the production line, XP-51. But this airplane was delivered to Wright Field sometime in 1941, fairly early, I think it was August. And they didn't have any plan for it, so they let it sit around a while. But there was an Aerts gun charger that was new, and they wanted to put it on some airplane. And so they put it on this XP-51, sent it to Eglin. And the report came back that this was the best fighter in the inventory. So that started things moving at Wright Field. They immediately ran some handling qualities tests, but in the meantime, in 1941, Bob Gilruth had pulled together the work of the 1930s that NACA had done in flying many different types of aircraft and having research pilots evaluate it in terms of the various handling qualities criteria or elements and pass judgment on them and try to set design goals or specification goals. And Bob pulled this all together, and it was published as a restricted report in April 1941 called Requirements for Satisfactory Flying Qualities of Airplanes. Now, the Army had supported this effort, so they sent this airplane here to Langley to try to corroborate those specifications and maybe extend them if required. The flight handling qualities test indicated it was an excellent airplane in terms of flying qualities, except for roll control. Now, roll control had been specified by the British. They asked for a PV over 2V of 04. Now, that's the helix angle generated by the aileron deflection as it screws through the air. It asked for a rolling velocity of PV over 2V of 04, rolling capability rather, at 400 miles an hour indicated, with no more than 50-pound stick force. Well, it didn't meet that. It was totally unsatisfactory at lower speeds. And when I got a chance to fly it later after flying a modified version, why, it was very obvious that it was difficult to even keep aligned with the runway with the low roll power that it originally had in gusty air. But at any rate, Bob Gilruth's gang went to work then at the request of the Army Air Forces to improve the roll control power of this airplane. What they did is see the original shape of the ailerons was this metal cusped surface, and the NACA overlaid that with balsa and then a metal sheet covering over that. So the bevel trailing edges, this angle governing the amount of balance, the angle between those two surfaces, were put on to alleviate the high hinge moments, and they increased the total throw of the ailerons by 100%. That is, they doubled the throw. To show, though, that you can't just do that without something happening, this is what was experienced with those ailerons when they were first flown at 320 miles an hour. Not only did they give a peculiar feel to the pilot as though the ailerons were going to snatch out of his hand, but when he turned them loose, they oscillated like this, which was totally unsatisfactory. So what they did is reduce the size of the bevel at the trailing edge, and put the geared tabs back in there, which had been there originally, and left the full deflection that they had opened up, plus and minus 20 degrees instead of plus and minus 10. And then they had very satisfactory aileron control. And as you can see from this chart I put together, the XP-51 originally was down in here, but it did not meet its 0.04 PV over 2V, even within the 50-pound stick force. Now, I don't know what you think about 50-pound stick forces, but I think that's awful high. It would cause internal injury for me in some cases trying to wrap it over this way. The NACA pilots preferred 30 pounds as a limit. Today it's 20 in the specifications. At any rate, the P-51H, after many modifications, that was the last of the P-51 variety, was still low, but the XP-51 up here was 09. Came down over here and satisfied this 400 requirement that had been laid down to start with. But this, you see, became the first Air Force specification for roll control effectiveness. And that was published in 1943, and .09 is still required for fighter aircraft, although today they start specifying it in terms of bank angle in a certain time period. The airplane in that configuration was a delight to fly. And might I point out, might I point out that that XP-51 with the modified ailerons is the one that the Experimental Aircraft Association has at Oshkosh in its museum. I got in touch with Paul Poveresny as soon as I learned they were picking up this airplane from the Smithsonian, and I gave him the information on the aileron so he wouldn't try to tear them apart and put them back in the original condition. But it has those originally bevel trailing edge ailerons on it still. Well, in the early part of the war, P-38s and P-47s began to run into this compressibility effect. First serious situations occurred with a P-38, and of course it had a great big elevator back there with no aerodynamic balance or power system in those days. And they would get into the tuck, and the buffeting was very severe, and they lost a couple of tail booms and tail and killed at least one pilot, and I think they probably killed two in dive studies. Later, of course, the dive recovery flap was developed and invented here at Langley and installed on many of these airplanes. But at that time, the elevator power was the only way to get out of it, and Lockheed eventually ended up providing hydraulic boost. But that didn't occur until the J models, which was downstream some. Anyway, when the P-47s got into trouble, and by the way, there were 3 P-47s in formation that went into Langley, or into the peninsula here, west of here, in a dive in formation. And I don't know whatever happened to the recovery of those, but they were locked into a compressibility dive and went right into the ground, 3 of them in a V formation. There were a lot of conferences and talks about why did the pilot think that he had a locked control when he got into these dives. Some said, well, maybe the hinges are binding under loads on the stabilizer. Maybe there's ice that forms up there in the high altitude, so forth. So they decided the flight tests were the only thing to do, and they instrumented this. The Republic instrumented it, and by the way, there were an awful lot of reports during the war of very, very high speeds approaching the speed of sound, and or even over the speed of sound. That was because the airspeed systems in those production airplanes weren't what we call balanced. The static side of the system had the altimeter and the rate of climb and the airspeed all on it. There was a lot of volume. Whereas the total head side, supplying the pressure side, was a very small volume. So in a steep dive where the pressure was increasing rapidly, the static side was much lower in pressure because it couldn't fill fast enough. So it gave erroneously high airspeed readings. So when they went ahead with these dive tests, they balanced the airspeed indicator so that they eliminated most of that, larger tubing, shorter lines, and that sort of thing. So they were reading approximately correct airspeed. All right. A Major Ritchie volunteered to do this. The company pilots couldn't be paid enough to do it. So a Major Ritchie, and they say he was the strongest pilot they had, he volunteered to do the dives. And so this is the dive of a P-47C to see whether or not the elevator moved when he put force on it. Make sure that his controls were connected and functioning. If they were, then it was an aerodynamic phenomenon. He entered this dive at something like 33,000 feet, wasn't it? And at 28,000 he turned on these records. But here's his Mach number rising. Here's his elevator position. And here's the load factor. He starts off at 1 G at this particular point in time. But as he crosses about 0.78 Mach number, there is a tuck. And he's pulling back now on the elevator. But the load factor comes up and starts down again, and he puts on more elevator. Here he applied at least about 200 pounds, and he affected only a half a G, but he didn't even recognize it because he's over on his back. And certainly, it didn't seem like very much to him. So then he eased off here, and the reason he recovered, oh, by the way, the Mach number is rising here, comes up and levels off at 0.86. But the reason he recovered is that the drag buildup at lower altitudes, due to his having shock on the wing, slowed him down. And that's the way many of these people in fighters throughout the war, the enemy as well as ours, recovered because of the slowdown due to drag. But 8.6 is as fast as we think anybody flew, except that there was an exchange in Aviation Week about this a couple of years ago, and the British claimed to have dived a Spitfire to 0.92 out of control. But this is out of control too. He couldn't control it until he got to lower altitudes. So maybe they're right. They got to 8.6 with no difficulty with their control, but to 9.2 out of control. So perhaps the Spitfire was the fastest. Now the Spitfire was much lighter than the P-47, but it had a thinner wing by 4%. By the way, it had NACA airfoil sections, 2212 to 2208 on a British Spitfire. Anyway, you can see what the situation was. So NASA, NACA decided they wanted more detailed information on the flow phenomenon and that sort of thing, so we instrumented an airplane. I guess you can't see it too well, but we had a tufted wing. This wing was fairly completely tufted. I've forgotten, the left one had some tufts on it, but it may not have been completely tufted. Here's a survey rake here to determine the momentum loss for that section of the wing at that point. I think we probably had pressure sensors over the wing surface too, I'm not sure, but we also had cameras photographing the tufts. And it was my program, and we get to 30, 35,000 and push over. Now, the only way we knew what the Mach number was a light that came on indicating a certain Q sub C over P ratio, which defines the Mach number. And when it got to a certain value, it would light a light on the panel. So this was reset for every dive. And we tried to get a dive that would not take us past that Mach number. We would set up a steady Mach number at about 20,000 feet, which took a little bit of guessing and care. Anyway, looking at the records, the airplane began to tuck at a Mach number of 0.71. However, that wasn't apparent to me. And at 0.78, bang, the thing nosed down, severe buffeting set in. The thing was, the elevator forces were pretty high, but not unrecoverable. And I made several dives in that region, 7/8 to 8/10. Coming home after one of these dives, I was flying over Newport News, and to Mach number 0.65 at 10,000 feet, this airplane, and I looked out at the left wing, and at about 15% of the chord, there was a tuft standing straight up and wiggling around like this, another one over here, not knowing which way to point. So I came back and asked Gene Draley, one of our aerodynamicists here, and he says, oh yes, we see that in the wind tunnel quite often. It's a separation bubble. The flow usually attaches behind it, so I guess that was a story, but I'd never seen one of those before. But when I looked out at the tufts on this wing, after the tuck, it looked to me as though the whole wing flow had detached and was just in uproar. The tufts were either standing straight up, pointing forward all the way from trailing edge to the leading edge, as far as I could tell. Of course, I was under stress at the moment, so may not have been exactly accurate. But that's the way it seemed. Now I want to show you what the P-47 was really like. I flew the C models, Ds, various Ds, and then the N. And it was one of our unstable airplanes, statically unstable. We had the whole CG variation here that we could get with 200 pounds of lead on the nose to try to make it stable. But it's totally unstable all the way. You push as you slow down from trim, and you pull like mad to keep it from tucking under at high speed. So the P-47, there was no difficulty in getting it into a dive, that's for sure. Well, here was another aircraft that gave a lot of trouble. It's the SB-2C. It went by various names, SOB. but it was one of our prime dive bombers, and the story is it never did pass its dive demonstration test, but they put it into service anyway. But it was very much unstable, too, and they wanted to use it on carriers, so the request of NACA was to provide a pull force to prevent the pilot from stalling the aircraft in his landing approach and landing. So bear with me here. Here is the stick force. Now, we put a tab on it that was spring-loaded to the up position, so that at low speed it would be deflected upward. And at high speeds it would fold back down to streamline with the elevator. Now that's what this tab lock means. In the original condition then, this aircraft, as you approach the stall, the stick force required was a push until at the stall my finger was against the instrument panel and it rolled off. The elevator angle is the same way, quite unstable, stick fixed. There's something else that's coming up. I want you to distinguish between stick fixed stability and stick free stability. Okay, with the springy tab operating now, that spring deflected upward as you slowed down, and it gave a stable variation of force with speed. So it did prevent stalling. Even though your hand for each trim position was moving up to the panel, it still required a pull force. The springy tab was doing this, up, and then would straighten out. So that seemed to solve that problem. However, I was curious about what this did to the dynamics. So I set the thing up at the same trim we had on the last thing and just disturbed it by 3 miles an hour in a push direction, and then turned it loose. And it built up very quickly into a large dynamic oscillation. That's because in order to change the spring, it had to gain some speed, the tab at the trailing edge. Now, this is an illustration of the fact that you can provide stick free stability, but not have the stick fixed stability will cause a problem. The sad part is, I think, that the FAA does not require in any airplane stick fixed stability. It requires only stick free stability. This is a big mistake because there are some general aviation airplanes flying today, one which they tried to certify at 25,000 feet that had stick-fixed instability, even though it had a device to give the stick-free stability. And that thing diverged so violently that it scared people in the certification process. And you've got other airplanes that aren't quite as bad, not quite as badly as that off. That was a poor piece of grammar. Quite badly off. They're flying with stick-fixed neutral or negative stability, but they have springs loading up the elevator so the trim tab provides the force, or the bob weights provide a force that the trim tab trims out. Now the trim tab position then provides a force that gives you stick-free stability. But here's a case, you know, the higher you go in altitude, the less damping there is up there to the rotary motions, and the more wild these gyrations would become. This airplane, by the way, this kind of a characteristic at low altitudes would just make the pilot work pretty hard because the airplane would always be tending to diverge. The P-63 was referred to Langley here because the pilots said they couldn't keep their guns on the target. This is normal acceleration, and the airplane was pumping in the turn. Well, with instrumentation, it turned out that it was related to directional oscillations and the side slip. And the side slip, the pitching moment that the side slip generated was the thing that the pilots objected to. So the solution wasn't very difficult. Here was the original fin, and we had this fin designed and built, which is of higher aspect ratio, and it catches more air, of course, as it flows by, and it's a little more area, I guess. But the Air Force didn't adopt it because they designed their fuselage strength to accommodate the fin loads to a certain side slip angle. And I guess the engineers here had a hard time convincing the Air Force that with this larger fin, it would never get to those side slip angles. so the loads would be less overall. But they never did adapt this fin. They put on some dorsals and ventrals eventually. Well, this is that same P-63, and many of these airplanes had lowly balanced elevators, and the force per G variation with center of gravity was of concern. In this particular aircraft, they went to the bevel trailing edge to balance the elevators, and it had a bob weight. And in plucking the control, it oscillated this way. This is a 39 as an illustration of a good response. It was heavily damped, so it didn't oscillate. But with the bob weight and the bevel trailing edges, it oscillated here. And note that the frequency is 1 cycle per second, right in the range where the pilot runs into trouble controlling these kind of things. So it was unsatisfactory. The pilot would pull and get too much elevator, and then about the time he was correcting for that, the bob weight would take effect and add to his input. That's the nature of the thing. And so that had to be corrected, and it was, in this case, by providing a little more force for the pilot through a spring hydraulic coupling to the elevator. Incidentally, I had a very serious case in an SB-2C. We were trying to lighten the forces the same way. In the hinge moment, I made a very normal takeoff, doing it gently. But when I pulled back on the stick and left the ground, see, the landing gear is trying to produce a moment nose down, and so there's always a tendency for this tail setter to sort of get off and nose up as you leave the ground. All of a sudden, I was out of phase with a very, very severe oscillation, and it scared the heck out of me. And what am I going to do? And so the next time I got the nose up, I just froze for a moment, stopped all this dynamics, and then very slowly moved the control. I was caught in a P-51 once at Mach number 7.5 in a dive, and all of a sudden this thing began to pump, and I couldn't stop it. I tried to freeze myself, and it wouldn't stop, because in an airplane, unlike some simulators, you're going up and down yourself, and there's no way you can stabilize yourself until you stop that elevator, and if you're coupled, you can't do it. So what I did is take my hands off the stick, the elevator stopped, then I took over again. But it took a lot of courage to turn loose that stick. You'll see some other PIOs later. Okay, now I was the first pilot to be sent through helicopter school. NASA, NACA here, had done an awful lot of work with autogyros over the 30s, and they were well-educated rotary wing people. So it was logical that the Navy and so forth would support Langley in studies of the helicopter and its rotary wing dynamics and aerodynamics too. One of those people is Al Gasso. He worked in that group at Langley. This is an NS-1, a variation of the YR-4B Navy designation. They were delivering the first one down here, and the Navy pilots were so enthusiastic they stopped by Pax River to demonstrate to a few people, and they found themselves with no wind out over the water and sank right into the water, and that was the end of that one. So they promptly got another one from Sikorsky and flew it down, so it arrived a little bit late. This thing was equipped, though, with torque meters for the main rotor shaft, torque meters for the tail rotor shaft, and flying qualities instrumentation to some degree. This boom was an airspeed head with a swiveling static that extended beyond the rotor diameter here, so that in slow flight, not necessarily hovering, or in slow flight, forward flight, you'd be in clean air, that is unaffected air, and the statics would head into the wind. We sort of varied instrumentation with time with this. These marks here are for getting altitudes in a hover series of tests to note the ground effect as the aircraft was at different heights above the ground. Generally, ground effect extends to about 1 rotor diameter. I want to talk about hovering. Hovering is a very strange environment for a fixed-wing pilot, and it usually takes 3 to 5 hours to check a pilot out so he can stay steady in a hover if he's just an airplane pilot. Now, that doesn't mean it's difficult, but he has to learn something new. And in the VTOL design of these early VTOL test beds, they didn't provide enough control. I don't think they appreciated the fact that hovering control is a high-order type of requirement. You have to prevent motion. To prevent motion, you have to provide corrective angular acceleration before anything else happens. So you have to sense things and be ahead of the game in the hover mode to stay fixed over a position on the ground. To illustrate what I mean, Charlie Zimmerman worked with low-speed aircraft, as you know, and he's an enthusiast, and he had heard me talk about hovering. He said, would you take me out on the H-13 and see? I'd like to see what happens. So I took him out there, and it was a nice steady day. We parked over the grass. He said, well, I don't see you doing anything. I said, Charlie, I'm doing something. So I said, now listen, got it all trimmed up. I'm going to take my hands off. Put your hands on there. I'm going to take my hands off. So I took my hands off, and he says, you've got it. And so it takes a little while to learn the fine control you have to provide to stay fixed. To provide that fine control, you have to have adequate control power in the aircraft. And you don't want to be searching it all the way to the corners of the cockpit to get it. And a lot of these designers have not appreciated that to start with. I think a lot of test beds have gone down the drain because they thought it was not a maneuver, so they didn't have to provide the control for the hover. They were providing it for the forward flight case, but that was a mistake. Okay. Our first efforts were with rotor performance, and this is an indication of the stall limits of the helicopter. You'll notice these lines painted here that show the scalloped fabric, and that's because these blades are really centrifugal pumps. They're pumping air out the tips, sucking in the fabric. And this white line is over a rib. This is displaced from the rib in between, you see. So, and these are the pitch things. But as the aircraft flies forward, and there's a high velocity on the forward advancing blade, but when it gets downstream, the wind velocity reduces its airspeed over here, so you have to rotate that blade or feather it to a higher pitch. You can approach the stall, and we were interested in when the stall begins at the tips and when it's limiting. And this is a case at 70 miles per hour where we started out, and at full power at 70 miles an hour, there's no stall at the tips. And then in slowly increasing the pitch at that same speed, then it begins to stall at the tips at about 12-degree calculated tip angle, and that's where your performance starts to go bad. And this is at 16 degrees where the rotor blade is stalled for a good part of its way out. This tuft here is going forward. This one's standing straight up. That one is still wiggling aft. This one's going outboard like a swept wing sort of thing. And so this was pretty badly stalled. The vibration was heavy. The stick was hard against the left-hand stop and about 1 inch from the forward stop. And that was considered the limiting flight condition for this particular rotor. It's published in Al Gassaw's book if you want to see how it looked. But it was very carefully approached by slowly pulling up the collective pitch, keeping the throttle full open. But during these performance tests where we were looking at high speeds and so forth and noting power required and things like that, I noticed that it was quite difficult to maintain steady flight. Now, everybody knows that the rotor advancing into the wind has a stability with respect to speed because the blade over here with high Q will tend to flap up and the one retreating will tend to flap down. So it's a stable sort of a pitch up. It tends to slow you down. But most of them overlook the angle of attack change. Anyway, so I decided to make some tests here just to get a handle on what was happening. So I just trimmed it up and made a step function there to disturb the machine, and it began one of these oscillations. This is at 40 miles an hour. It expanded and interested me because I said, well, what's going to happen at a higher speed? So we tried it at a higher speed. And this is at 65 miles an hour. And here's a little step function again. The aircraft noses up and then noses down and is diverging. I put in a good deal of control, and then it starts diverging upward. I slammed the control against the stop, and it still continues. And in there somewhere I jammed the pitch down to the minimum and rolled off over the top. But convinced me and other people that there's an angle of attack instability, which is much more powerful and more important than the speed stability. It had to be dealt with. Well, the way we dealt with it, we didn't try to work with the R4, the HNS-1, but the Navy was interested in our handling qualities work, provided this HO-3S, which was the Army R5, S-51 commercially. And it diverged just like the R4. I remember taking Hack Wilson for a ride, and I got it all trimmed up at 80 miles an hour, and I said, now watch, Hack. 3 seconds I had to take over because it had diverged to a serious nose-down position. But anyway, we put a tail on here, and that stabilized the aircraft. If you stabilize the fuselage, why, the rotor will respond to that stabilization and maintain a constant attitude. We later hooked it up to the longitudinal control. And then we had an elevator combined with the helicopter, the feathering of the rotor. We did a lot of helicopter handling quality studies in the basic helicopter, and then had a hydraulic system installed and eventually electronics to make it a variable stability aircraft. And then we went to instrument flying, and I missed a step there. I wanted to say that in the early days when we had these sticks that walked around in the cockpit at 1 per rev, they shook, vibrated, we couldn't get data on stability in turns or in the the maneuvering stability, because the stick was rough, the stability was so low that we couldn't get measurable deflections that weren't hidden by the hash, the vibration. And besides, the drag was high, and it took a very steep wind-up turn to keep the speed up. So we went to the pull and hold, a step pull and hold, and in measuring the response to that, it either leveled off or it diverged to undesirable degree. And that went into the original handling quality requirements that we set up with the Navy. I don't know whether it's still there or not, but a lot of people misinterpret that. It's really a measure of angle of attack damping combination at these forward flight speeds. It's not a measure of the oscillatory frequencies or anything like that. It always occurred to me that here's a helicopter or an aircraft that can fly at very low speeds, and it might have extreme utility if you could develop the ability to operate in low visibility. So we began to look at this. Now, there's some problems in low-speed helicopter flight. One is that at 25 knots, if it's upset 5 degrees in bank, it'll develop the same rate of turn as an airplane flying at 120 with a 30-degree angle of bank. So it will turn off course very rapidly. Secondly, at low speeds, you're on the backside of the power required curve, which continually requires adjustment of power. And when you do that, you put in the need for a correction in torque or yaw. So it becomes a handful. I want to point out that flying a specific path through the air is different than dunking a sonar, because in a sonar you can come on down there without following a specific path through the sky and dip it and hover, and that's a fairly easy task. When you attach it to a specific path through the air, you've got a very much greater task and workload. Anyway, this is the first use of a zero reader, and we did an awful lot of flying with this thing on our own generated GCA and also on ILSs and things like that, published reports. But the thing that's disappointing to me is today they're still operating helicopters like an airplane. 60 to 80 knots on the approach, 3 degrees, 200 feet and half a mile for an aircraft that really has the potential for safe operation and very low visibility. And the technology for flight systems today, or flight control systems, is here. But they don't seem to want to use it. I guess costly, but in the long run it would pay off. Well, Langley continued with this, as you'll see later. Am I running out of time?
Oh, I think that's fine.
All right.
I think you're fine, Jack, but we, another 10 or 15 minutes.
Okay. Okay, well, we looked at the tandem too, and the tandem helicopter was unstable with speed, unstable with angle of attack, unstable in yaw. So it didn't care which way. It would rather fly at 90 degrees to the wind than straight ahead. And we began to look at some of these problems. I went up to Pax River. We used to have very close relationships with the rotary wing branch up there. Went up there to fly the XHJP, which is one of the tandems that had squeezed up and had the high pylon on the rear. And I came back and talked to Johnny Campbell, and I said, my gosh, that thing's so directionally unstable, I can't keep it within 10 degrees of the heading I want to fly. How could you navigate? So he did some wind tunnel work and found out that there was flow separation on this thick pylon back there. And he tried in his model, flaring out those sides so they came straight back and ended with a flat back trailing edge. And that was that did stabilize the helicopter. Later on, I don't think they did use that in service for a while, but they ended up with extending the trailing edge of that fin also. But anyway, this was just a test bed to find out how to cope with some of these things. The C-54 was sent here by ATA for an evaluation of its handling qualities. This is just after the war, 1946. They were interested in lower weather minima and handling qualities to support lower weather minima. The airplane was a good airplane. Control forces were high. I like to fly with one hand and the other one on the throttle because that's the way I best coordinate. I don't like to have to wrestle two hands. This thing had those kind of high forces. But the friction in the servo system, the autopilots of those days didn't couple with ILS or anything. When you made an instrument approach, you turned them off and the servo units moved with you. Well, they produced 12 pounds of friction in the aileron system, and when they were disconnected, the precision was very good. But it was a matter of friction in the control system. And this airplane interested me in pursuing a program for instrumentation for lower weather minima on the precision guidance systems that they were bringing in, like ILS. However, I was told that was the prerogative of FAA, so we didn't do anything at the time. My interest was raised. Here's the P-63, the Navy's swept wing study. They were going to put swept wings on the carrier. They wanted to know what sort of problems to look for. This is a 66 series wing. No geometric washout. There was a little bit of aerodynamic washout. But we had three versions, no slats or two slat arrangements that were of different span length, and two vertical fin areas. Well, the dihedral at low speed was very high. At 200 miles an hour, the dihedral effect was about zero. We measured rolling moments by loading the fuel cells. There was one over here, and one in the nose. We burn out one completely and burn off the nose, and we could get rolling moments directly by approaching low speed or in any kind of a maneuver. One day I was interested in whether the ailerons would produce stall on the up or down side. So I carried one to the stall, and it rolled with the ailerons, as I thought it should. But a lot of people are always afraid to use ailerons near the stall because they fear that the ailerons will stall the wing, which has never happened in my case. B-29, we used it for drop models, as Hewitt Phillips mentioned. Also, we had one that we put a boost control system in it. And we looked at the range of control forces for longitudinal and lateral. Airplanes like this had 120 pounds per G at cruise and 90 pounds per G at low speed, which is kind of high. We like to see 20 to 30 in my case. But anyway, one day they made a mistake. They let me fly it with 6 pounds per G and 1 pound per inch of control wheel force in the longitudinal direction. And I really enjoyed that. Fingertip control down an ILS or to a landing. Why, that was the best thing I'd run into in big airplanes. But I don't know, some people just object to the low forces. I learned also that with the inertia of an airplane like that, the time constant is quite high. So if you do over control, you would detect it well ahead of time and make the proper corrections so you don't exceed any G that you don't want to. So it had compensating features, but I really enjoyed light forces. I want to coordinate these two without effort. If you've ever tried to manipulate a 50-pound force with one arm, pick up a sack of 50-pound seed or something like that and try to bring it up here and put it down very neatly and gently at a specific spot. You're struggling, you know, and I'd rather have easy control where I can coordinate the throttles and the elevator combined, and ailerons too. This airplane also had an aileron deflection, a wheel deflection from max aileron of 180 degrees. Now I ask you, who can put 180 degrees on a wheel while you're flying an approach? So that's the way they got apparently light forces, but you had to go to very large wheel deflections for maximum. This is an F4U4, and I'm going to talk about something Hewitt talked about. They had this hydraulic power system in here. You could switch from manual to hydraulic power, and they were doing some things, and I thought I'd go up and see what the characteristics were when you try to rapidly enter a turn. And so I selected a 3G turn, which was okay with the elevator, but here's a case where I apply a stick force to open the valve. The valve opens, and then it's apparent the airplane is going to shoot up like that. So I center the valve and stop the flow, but I've gained a little bit of elevator deflection, and so forth, all the way down the line. So it took me about twice as long to wrap into a 3G turn with this kind of a characteristic, which would PIO generating kind of characteristic. But all the time you felt you were on the pin of a needle. You might fall off and wreck the airplane or yourself. Now to cap this, here's a real PIO. This was in an T-38, and it has a pitch damper on here, but the pilot turned it off there. Now you'll note that this one is 1 cycle per second again, the natural frequency of the pilot, where he finds himself unable to adjust the phase. And this airplane oscillated between 8 plus and 8 minus G here for quite a period of time, and I don't know how he regained control. But the Air Force bent 13 airframes with this kind of a PIO, and then they made a tour of the industry and us and so forth to find out what you could do about it. I think the only thing they did was to put a much stiffer spring on the valve. It was traceable to valve friction. And but then the maneuvering forces get to be high. I want to explain, PIO is not easy to deal with because when you're being thrown up, you try to put in a command and then wham, and you're hitting the ceiling with your head or against the straps, and then you're being slammed down into the seat, and it's very difficult to apply a small corrective action to stop this thing. Even in the demonstration, I was out of phase. But a PIO is not to be laughed at. It's a very serious situation when you encounter it, and you hope you never see it again. This is an F9, F2. The flight research gang looked into fly-by-wire systems back in that period of time. And this is an F9, F2 jet Navy fighter. We had put the electronics in it. This shows one control arrangement. We looked at rigid sticks in the center, on the side. This is a displacement stick with the arm resting on this pad, and you use your fingers like a pencil. That was the most liked control system arrangement. Pilots would fly at altitude, maneuvers, and come back and make takeoffs and landings with that, and like it very much. We had rate command, attitude command, and normal acceleration command, and they all liked the rate command as best. It was hiding at one time. It was hiding a center of gravity 4% after the maneuver point, and I was curious, so I turned off the electronics to see what it was like, but I slowed the airplane down so if it stalled, it wouldn't break the wings, and it was scary. That flying 4% back of the maneuvering point meant that the airplane was trying to diverge, and it felt like a hard sell. I was scared. I flew there for a little while. And if you let it go too long, you had the feeling you weren't going to be able to check it. We had a sack of BBs in the back. We could pull a ripcord and dump them to move the CG forward, so there was that escape. This was our last high-performance airplane. This is 58. We got 2 of these F8U3s, and all the spare parts they had, a chance bought. to continue high-speed research. We did do sonic boom work with it at Mach number 2 at 60,000 feet. But then we had to get rid of it. They used it for target gun firing, see what damage you could do with gunfire on the fuselage. Sad. But we had to get rid of it, and all of our airplane programs disappeared. And we were limited to helicopters, VSTOL, and necessary transport. Well, Lockheed decided to build a helicopter, get in the helicopter business. They built this one for Grandma to go shopping in, as they put it. And in this first version, they requested my evaluation through my boss, and so I went out there and flew this thing. It was a hingeless rotor. We had some experience with hingeless rotors already in one of our own designs. And this ring around here was a gyro, and the rotor, of course, is a gyro. So the control system put a spring force on this rotating gyro to force precession, and that precession feathered the blade. One year, I think it was, the junior year. And we didn't get very many flights. Most of the time, the glider was being worked on. But first, they held us up in a strong wind at the wingtips, and we operated the controls to see how they functioned. And then we towed by truck. Well, on my first tow, I had been used to steering a bobsled, where you turn the front sled in a certain direction. I had read a lot about aviation, all the books, Wolfgang, Langley, and Stick and Rudder, you know, and this sort of thing. But the thinking couldn't overcome the habit. And so I started down this runway doing all the wrong things with the rudder, and the first thing I knew, I was airborne. And then I could give up the rudder and flew it with the stick cast off and glided gently towards the runway and just eased back the stick and landed. So I got over my fear of soloing on the very first flight, which I'm thankful for. Let's see, at the University of Michigan, I did join this glider club. Could I have the first slide, please? One of my friends and cohorts took this picture as I was landing one day. Looks as though I know how to do this by this time. The little white thing in front of me there is the airspeed indicator, just a flat plate mounted on a spring, and it read along a scale. But you could take that nose off and be out in the open. Well, I never did proceed to soaring. They did soar in the summertime with this thing. Next slide, please. I'll learn. When I arrived here at NASA, by the way, the professors had been coming down to Langley here, some of them, to the conferences, but also to work. And they were very enthusiastic. They selected 3 University of Michigan people along with 3 MIT in that selection. NASA had just gotten authorization to expand. This is the early part of the buildup of German forces in Europe. And the new labs were yet to come, but they had just begun this, and they were recruiting for the first time. And I got here on June the 2nd. Some of my MIT friends got there June the 1st. But I reported out to Elton Miller, and he said, "Now, where would you like to work?" I said, "I'd like to work in the flight division." He said, "Sorry, we've got you slated for the full-scale wind tunnel." So there I spent 4 1/3 years. This particular airplane is the Brewster XF-2A1. It had won the competition over Grumman for the Navy's first carrier monoplane. And it had had such poor performance that the Navy had asked NACA, I'm sorry, I've had more years at NASA than I have at NACA, I forget sometimes. Anyway, they asked NACA to put it in the full-scale tunnel and look for ways of improving the performance. Well, they found a lot of them. The cowling was poor, the carburetor intake caused separated flow, it had high drag, and so forth. And the interesting thing is, it was just being completed when I got there. And after that, some 30 aircraft, military aircraft, passed through this tunnel for improvements during the war years. But this was the first one. And later, of course, Brewster lost failed to produce, and Grumman, who had continued to build the F-4F despite losing the contract, really took over, and the F-4Fs were the aircraft produced in quantity. It's interesting that the second airplane tested in the tunnel after this was Grumman's latest biplane, the F-3F, and it was 115 mile. No, it was a. Well, it was 25 or 30 miles an hour faster than this monoplane. Next. Oh, I'm sorry. Well, during this period of time in the full-scale tunnel, by the way, they had about 6 landing fields, civil landing fields around here, but this landing field is where the Copeland Industrial Park is today. It's really in Hampton, but it bordered on Newport News. We had learned to, we had bought this airplane and flew it out of Morgan's Field, where the military highway down here, Mercury, crosses the Langley Field Road. And however, the man who owned it got rid of his cows. The grass grew too high, and it was an arresting gear and made it pretty hard to take off because the engine seemed to burn grass seed. So we moved over to Newport News, where they had some hangar space. This is really one of the early fly-by-wire aircraft, because it had cable control, of course. Well, this is a little premature, but I'll leave it on. During 1941, Melgoff, chief test pilot, detected the fact that it was becoming difficult to get the kind of trained pilots that the military forces were producing, and he thought that he'd better make some provision for supplying and retaining the staff of test pilots that the Langley Center had, considering that Ames was requiring pilots, Cleveland was requiring pilots, and those are both being activated in 1940, 41, 42 time period. So he wrote a memorandum asking permission to select some pilots or some engineers who were eager to fly and were best qualified to be taken on board as trainee test pilots. Now, bear in mind that there were no test. Anyway, I was born in the Upper Peninsula, Michigan, and of course, my dad was a mining engineer. There's copper and iron up there, and I saw very few airplanes. We moved to Canada, though, for 2 years into the nickel region around Sudbury, and some great big old biplane flying boats of World War I, namely Curtiss HS-2Ls, were bought by or given to the Canadian government by the U.S., and they used them for forest fire patrol. And I could hear these things coming low over the forest. We were out away from the city, and these guys would fly by at about 200 to 300 feet, and the observer in the front, which used to be a machine gun position, would wave to us kids down. Well, kids, there weren't very many kids around me. Most of the time I was alone. And I'd wave back and so forth and watch it go off, and they'd repeat every 2 or 3 days. And that's when I really became interested in flying. Moving back to the Upper Peninsula, I used to attend some of the Michigan Air Tour shows, where there would be a collection of airplanes, but I was quite fascinated. By the time I was in high school, or 9th and 10th grades actually, I had decided I wanted to be an engineering test pilot. But I realized I had to get an aeronautical engineering degree, and then I wanted to proceed to the Navy flight training, because the Navy operated more types of aircraft than the Army did. Well, it didn't all quite work out that way. I did go to the university and entered in 1934, aeronautical engineering. And during the course of those studies, I wasn't a very brilliant engineer, by the way, but during the course of those studies, I sneaked. My dad wasn't exactly enthusiastic about me flying. But anyway, I did join the glider club for about, Am I loud enough? All right. Thank you. Well, Thank you very much, Jerry. That was certainly an impressive introduction. Hope I can live up to it. I'd like to start off by telling a little anecdote about Hewitt Phillips. A short time after I joined the flight division, and he was researching yawing oscillations of aircraft. He had set up a simulator in which he could vary the frequency of the oscillation and restoring forces. And the pilot was supposed to try to damp these oscillations with pedals. And I was one of the subjects, not the only one, but I got in this day, and they'd pluck it and the thing would oscillate, and I'd try to get out of phase with this thing in order to damp the motion. And I found that I, 9 times out of 10, or 50% anyway, I amplified the oscillation. So I decided to wait until this thing got to its maximum amplitude and then put on full pedal till it stopped. Well, I did this about twice, and there was a bang and bang, 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 bang. All the springs from this thing flew all over the hangar. And Hewitt came up to me, a little bit red-faced, and he said, "That's not the way you're supposed to control it."